Welcome to the ASMR chemistry classroom. We are going to do some kinetics today. We haven't done kinetics in a long time, so I think it's time we delved into this wonderful realm of dynamics of molecules. And specifically, we are going to focus on collision theory and the Arrhenius equation. Okay, so I'm so excited about my collection of pens that I'm getting, my fountain pens. But because this is my newest one, I'm going to use this one. Okay, so let's talk about collision theory and kinetics. Okay, so just start out with the big picture here. Kinetics. So we're talking about how fast reactions happen and also details of how they happen on the molecular scale. How are these molecules coming together? How are they changing to then ultimately create the products? Okay, so collision theory. These are the postulates that we talk about that are relevant to kinetics. And in terms of this word collision, it is literally the molecules are colliding. Okay. Now, sometimes it's a molecule breaking apart, not colliding. But collision theory is the term that is used for this whole idea that is more of a conceptual approach to how molecules are coming together and reacting. Okay, so the postulates. We'll talk about these and then we'll look at the Arrhenius equation and do some calculations. Okay, the first is reaction rate. This means proportional to, okay, number of collisions over time. More collisions in the same amount of time, faster reaction rate. Okay, what else? The reactants must collide with proper orientation. You can think of Lego pieces. When you pop together Lego pieces, they have to be in the correct orientation to snap together, right? And the reactants must have enough energy. When they collide, they can actually react. We can actually think about the Lego example with this as well. That would be if you just held two Lego pieces together but didn't push them together, they wouldn't snap. But with enough energy, push them together and they snap together, right? Okay. So from these postulates, we can definitely see that there are two things that we can control pretty easily and very commonly to increase the reaction rate or influence it. You could even decrease it if you wanted. And one is temperature that is going to change the number of collisions over time, because when you increase the temperature, the molecules are moving faster, so they're going to collide more often, right? Also, when you increase the temperature, the molecules are going to have more energy, so that when they do collide, there's a higher chance that they will actually react. Okay, so temperature is a double whammy in that sense. Okay, concentration. If you have a higher concentration of molecules, then you'll increase the chance of collisions, right? Also, if you have a catalyst can sometimes help with having the molecules be in the proper orientation. And another role catalyst can play is to provide an alternate mechanism that gives a lower energy barrier for those reactants. So it allows an influence on postulate number 3. So it depends on the type of catalyst that you have. Okay. So let's move things over, because I want to now talk about how we can mathematically describe these ideas. And that is the role of the Arrhenius equation. Okay. So our Arrhenius equation it's not as important that you know the name of the equation as you do when you have the equation, you know what it means and how to use it. Okay, so here we go with all the pieces of the Arrhenius equation. All right. Now I'm very tempted to use another color here. This is actually dark purple ink I'm using. I'm gonna see do I have my blue handy? Oh, my red leaks, so I'm not gonna use that one. Okay. This is a rate constant. Okay. The units depend on the order of the reaction, okay? But the main thing we want to focus on right now is acknowledging that a larger rate constant corresponds to faster reaction, okay? All right, what's this A here? Okay. Move this up. Went to my room here. Okay. This is the frequency factor. This is related to this idea of orientation, and a larger A value, this corresponds to higher probability of the molecules colliding with the correct orientation. So I'm going to try to write this concisely. Correct orientation. that can manifest itself in various ways. One could be perhaps you have a molecule that has 4 different sites where if it collides at those sites, that can result in a reaction. Perhaps it's a larger molecule, or in some way there's a higher likelihood of that correct orientation resulting in a reaction. Okay, now we've got up here activation energy. And this is the energy barrier. Are we fitting here? Okay. This is energy barrier. For the molecules to react. How much energy do they need to actually react? Okay. And so if you have a larger activation energy, that corresponds to a larger, if that word barrier is helpful, right? And this would mean that the reaction would happen more slowly. Okay, larger barrier. Fewer of the molecules will have enough energy to react. That slows the reaction down. Okay. Also in this equation, we have gas constant, and this is in the form of joules. Not, oh, I'm sorry, that's out of the okay. This is 8.314 joules per mole Kelvin. All right. And here's our temperature. This must be in Kelvin in order for our units to work out. Okay. So as a explanation a little bit more about activation energy, I wanted to show an energy diagram of the sample reaction. And let's just look at energy overall. We can get into specific types of energy, but let's just say overall energy and the reaction. And if we're looking at reactants, go into products. So this is, if you're looking just at enthalpy, you may call this exothermic. If you're looking at overall energy or Gibbs energy, exergonic is a term. But this would be a thermodynamic point of view. What was the energy overall in the beginning? What's the energy overall in the end? But with kinetics, we now bring in this aspect of activation energy, which means that the reactants aren't going to just fall down to this lower energy level and release the energy, but instead they actually need to have enough energy to make it over this barrier, this energy barrier. Okay, it's actually a good thing, or else chemical reactions would be happening everywhere all the time. There wouldn't be a lot of stability with any materials or even living things. So activation energy is a good thing. But here is where we would show the activation energy. Get, I'm going to try my red pen, even though it leaks. I'm going to just use it for this one thing. Okay. So the activation energy is from the beginning of where the reactants are, that energy, and it goes to the top of this barrier. That is activation energy. Okay. Larger activation energy, those reactants have to have more energy to make it over. So larger activation energy, slower reaction. Smaller activation energy, if it were down here, it's going to go faster. More of the reactants will have enough energy to hop over and become products. Okay. All right, what do you think? Shall we do a calculation so you can see how it works? Let's do it. Flip this paper over. Okay. All right. Let's do an example. Calculation. Here is, I'll write out the Arrhenius equation so we have it handy. I almost started writing Arrhenius, but frequency factor. I'm guessing that this frequency factor was named after Arrhenius. I don't really know, just speculating. All right, there's our activation energy, gas constant, temperature. So let's look at a case where, for a reaction, it's known that the value of the frequency factor is 4.0. It's 10 to the 17th per second. Okay. These units, this is consistent with a first order reaction. It is also known for this reaction that the activation energy is 110.36 kilojoules per mole. So then the question is, what is the rate constant at 298 Kelvin? Okay, this is room temperature. All right. So, because we know that the gas constant is given to us in kilojoules per mole, the gas constant is given in joules per mole, but the activation energy was in kilojoules per mole. That means we need to either convert activation energy to joules per mole or the gas constant to kilojoules per mole. I am going to write out what the gas constant is, and then you can make your choice of which you prefer. Okay, so oftentimes in textbooks it's given in 8.314 joules per mole Kelvin, but that is equal to maybe I'll put the equals there, 8.314 kilojoules, times, that's what I meant to say, times 10 to the minus 3 kilojoules per mole Kelvin. So a lot of times I'll just acknowledge that in kilojoules per mole, we would multiply by 10 to the minus 3 to give those units, and then it will work out with activation energy. Okay, so keeping that in mind, let's do the calculation, okay? So, I'll move this up and I'm going to rewrite our equation. Here is our Arrhenius equation. Okay. We were given what the frequency factor is. Times 10 to the 17th. By the way, really large values like 10 to the 17th are pretty common for the frequency factor. Okay. Then we have our E. And here's our exponent. We've got a lot up here. We've got our 110 kilojoules per mole. Okay, and then we're going to divide that by 8.314 times 10 to the minus 3 kilojoules per mole Kelvin. Okay, I want that kilojoules to cancel out and the per mole to cancel out. And then we put in our temperature. This is also in the denominator, this whole thing. 298 Kelvin. Okay. So 110 kilojoules per mole. We will see kilojoules are going to cancel out. We're going to have per mole cancel out. And then here we have Kelvin, and here Kelvin is in this denominator, so Kelvin's going to cancel out. And so this entire exponent is going to be unitless. All right. Okay, we put in our values. So sometimes, depending on the calculator I'm using, I'll calculate the exponent first and then raise e to that value. Sometimes I'll just put it all in. Okay. So 10, make that negative, divided by 8.314 times 10 to the minus 3 divided by 298. Okay, and then e to the x of that, and then times 4, 10 to the 17th. Okay, we have 2 sig bigs in our final answer, and it is 2.1 times 10 to the minus 2, and that is per second. Okay, so again, the units will be consistent between the frequency vector and the rate constant. So here is our final result. So if you want to practice, one thing you could do is pause the video and go back and try calculating it yourself with all of these values that were given and see if you get the same answer. Okay, because sometimes calculators can be squirrely. Different calculators have different ways of inputting the numbers. So it's really important that you get to know your calculator really well and getting that final answer. So I say that because it is pretty common that I will have students come to me sometimes during a quiz or during an exam, and they will ask for help with their calculator, with some things like exponents, with natural logs, and things like that. So very wise to get used to your calculator and make sure the batteries are functional before you go into an exam. It's unfortunate how many times calculators go awry during exams. Okay. One last thing I want to go over is how you can determine activation energy. Okay. Now, you need to collect, as usual with kinetics, you need to collect data. You need to go in the lab and actually get some experimental data. But how to collect, or how to determine, I should say, that activation energy. How do people do that? Okay. So if you take the Arrhenius equation and you imagine that you are measuring rate constants, I'll just refer to it here. If you're measuring rate constants at different temperatures for the same reaction, you can actually divide two equations by one another. And what you get when you do that looks like this. Natural log of the ratio, because rate constant will change with temperature. Okay, you'll have, at a higher temperature, you will have a larger rate constant. Okay, so the ratio of the rate constants at two different temperatures, natural log of that is equal to activation energy divided by gas constant, and that's multiplied by reciprocal of one temperature. This is T2 that matches what the rate constant would be. Okay, and minus T1. Okay, now you can solve for activation energy. That might not be your favorite thing to do, but guess what? I'm gonna give you what the result would be. It is, if you enjoy algebra, it's kind of a fun thing to do, but we're just gonna go straight to it and solve for EA. All right, so when you rearrange algebraically this formula, you get that activation energy is gas constant times both temperatures multiplied together divided by the difference between these two temperatures. Okay. By the way, I'm assuming that the T2 is the higher temperature. Should work out either way, though. And natural log K2 divided by K1. Okay. Alrighty. Let's do an example, okay? Let's look at this reaction here. I'm going to move this up so we have got some room here. This is for the reaction of nitrogen dioxide that can break apart to form nitric oxide and oxygen. This is all gas phase. Okay, and it was determined after some measurements that the gas, I'm sorry, not the gas constant, the rate constant was 0.24 molar to the minus 1, seconds to the minus 1. Ooh, that tells us it's second order. See how the units of the rate constant are different than what we saw previously? That's because this must be a second order reaction. Okay, anyway, this is what the value is at 573 Kelvin. Meanwhile, the rate constant, and don't you love how it has the term rate constant? But now I'm telling you it's a different number. So rate constants are constant at a constant temperature. But if you change the temperature, look what happens. Oh my gosh, this goes all the way up to 102 molar minus 1, seconds minus 1. This is at, and you could already guess, this is at a higher temperature. This is at 773 Kelvin, 200 degrees higher. Okay, so now if we want to determine what is the activation energy for this reaction, we can put in all these values. Okay, so let's put them in. Activation energy equals, all right, here's our gas constant. 8.314. Let's put it in kilojoules per mole times 10 to the minus 3 kilojoules per mole Kelvin. That's what I meant to say. Okay, so that's what we just put in here. Here's our gas constant. Now we're going to multiply each of these temperatures. We'll put in the 573 Kelvin and the 773 Kelvin. All right. Then we will divide by the difference between the two. 573, 773. Okay, the difference between the two is 200 Kelvin. I'll put that there. And that is 3 significant figures. Since we have 3 here, we subtract them. And so these zeros are significant. Okay. We're so close. Now we just need to include that natural log portion. So I'll move this over. Get some more room here. And so now we have natural log. And how did we define these, right? We had 773 was T2, so that's K2. We want to make sure these match. And this was K1. So we're going to take the ratio of 102 over 0.24. These units are the same. They will cancel out. We can just include them just to show that. Okay, so units will cancel out. We'll take natural log of this unitless number. Okay, natural log of, see this ratio? This is going to end up being greater than 1. Natural log of a number greater than 1 is a positive value. This here is a positive value. If we were to reverse and say T1 minus T2 is minus 200, we'd have a negative there. These would be inverted. Then this would be a fractional number. Natural log of a fractional number is negative. So we would still end up with a positive activation energy. So it works out either way. Okay, just make sure you keep them straight. Which one you're calling 1, K1, that goes with temperature 1. K2 goes with temperature 2. Alrighty, put in these values. Okay, and we get 102 you should always get a positive value for your activation energy. Okay? Always positive value. All right, and that corresponds to that diagram, that graph that I showed you before, where we're looking at a reaction, energy, okay? And we saw that we had to go over that barrier, right? This is positive. We're going up in energy. We need an input of energy to make it over the activation energy. So this difference here in this case is 111 kilojoules per mole. Okay. Your activation energies will always be positive. Okay. So if you get a negative value, then you did something, probably with taking the difference between the temperatures or something like that. So that's something to watch for. Whew, that was a lot. We just went through a lot, right? We talked about kinetics generally. We talked about some of the concepts of collision theory. And then we tied in collision theory mathematically with the Arrhenius equation. We did an example calculation of using just the Arrhenius equation, and then we went through and we solved for activation energy with the fundamentally starting with the Arrhenius equation. And from this equation, we then took some data that someone else collected and we calculated activation energy for that reaction. So, I hope this was helpful. Hope it was either helpful for you learning about collision theory, Arrhenius equation, activation energies, or by now you are fast asleep. So, either way, it's a win, right? Thank you again, as always, for being here with me. Thank you for supporting this channel. Please do like and subscribe if you are enjoying it. It helps me so much, and I am planning on having this channel grow and posting more videos and creating more, and also improving the quality of the video and the sound and everything else I can do that will help you. And anything else that I can do, let me know. I am here for you. I love doing this, and I will see you next time.